I want to tell you about an algorithm that I hope you'll think is as amazing as I do. It transforms your written description of what you want a circuit to do into a circuit that does it, and it scales to circuits of any size, and best of all, it saves you the trouble of having to worry about any internal timing issues. So I will, for about the first half of the talk, give you some background material, and then we'll get down to business. So let's start with a logic puzzle. Suppose a committee of 3 people is going to vote on a series of motions. Each committee member controls one input to this machine whose purpose is to indicate when a motion passes by simple majority. The idea is that if any 2 people vote for something, the corresponding AND gate output goes up, which pushes up the overall output. So it seems very simple, but here's a question. Could this circuit ever report incorrectly that a motion has passed when it hasn't gained a majority vote? Of course, anything this simple, there has to be a catch, right? It has to be a trick question. Well, there is a catch. The catch is that after each vote is taken, the committee members have to stop voting long enough for the circuit to return to its initial state. We take for granted that a circuit like this is going to follow a 4-phase or return to 0 protocol. But suppose A and B both vote for something, the output goes up as it should, and then they stop voting, maybe not at exactly the same time. A stops first, B is still voting, the output has dropped, and now B stops, and the output hasn't changed, and for a brief moment after that, the circuit hasn't settled down internally, even though all of the inputs are low. If something else were to come up for a vote during this time and only C voted for it, we could get an incorrect result. Does anyone want to say that this could never possibly happen? Okay, so we're all on the same page. What do we do about this then? Well, if the circuit were to maintain the output until it had reset internally, then we might stand some chance of interacting with it reliably. So to that end, we could use a join instead of an AND gate, also known as a C element. Like an AND gate, the output of a join goes up when both inputs go up, but unlike an AND, it stays up until not just one but both inputs drop. You almost don't have to pay attention, if you don't want to whether the output is high or low. You could just pay attention to when it changes. Then you'd be following a 2-phase or non-return to 0 protocol. And in that case, you'd probably want to use an exclusive OR on the output rather than an OR. But we could just call it a merge and draw it like this to emphasize that we care about it merging multiple streams of signals into one stream rather than any particular logic function. So now, if A and B both vote for something, the output X goes up, and A stops voting, B is still voting, the output is still up, better than before. And now when B stops voting, the outputs are all low. The circuit still hasn't reset internally. How did that happen? Well, nobody said both sides of this fork have to have the same delay. So if something else comes up for a vote now and only C votes for it, we have the same problem as before. If you think that you can correct this circuit by adding more completion detection logic onto it, you'll find that it's impossible. Some people have reached this point and said, clearly we're at an impasse. We just have to assume that both sides of this fork have similar delays, not because it's true, but just because. This assumption is known as the isochronic fork assumption, characteristic of quasi-delay-insensitive or QDI design. To justify it, you have to control the layout and the geometry of the circuit, and you have to solve physics problems. QDI designers are correct when they claim that it's impossible to avoid isochronic forks if they restrict themselves to circuits built from single output devices such as logic gates, but it has been known for at least 25 years that useful asynchronous circuits can be built from other primitives than logic gates without any further need for isochronic forks. So what are these other primitives other than, yes?
I'm wondering if the problem is that you've got only 2 outputs, true and false. But really you need three, because, or perhaps you could do better if you had three. One to say result, motion is passed, result, motion is not passed, and another one is off.
Yeah, there is. I thought someone might ask that, so I have some slides prepared for it at the end. The right way to do this as a delay-insensitive circuit would be using a dual rail code, because you can't take the absence of a yes to mean no. Right. So you'd have one wire for yes, one for no, and then it wouldn't solve this problem with isochronic forks that I've mentioned. You would still have to do some of the same stuff that I'm going to talk about now to get around it. So anyway, I was going to talk about these other primitives than logic gates. What are they? Nothing special, only 7, and you've already seen 3 of them. Of those you haven't seen, the toggle takes a sequence of one input signal after the other, and then it acknowledges them alternately on one output terminal and then the other. The arbiter has 2 passive 4-phase handshaking ports and will allow a handshake to complete on at most one of them at a time, blocking the other if necessary. A push is just like a wire, except when you first power it up, it emits an output signal before receiving any input. It's used for initializing things. And a shunt is a memory or state holding device, about which I'll say more later. Now, if you're going to build circuits out of components like these, your usual techniques of Boolean algebra are not much help to you. So what could you do instead? Well, you could start by using a Petri net, following a convention where some of the transitions in the Petri net are labeled, inputs in green, outputs in red, and usual firing rules apply. And we also have a convention where we assume that only the labeled transitions are observable. Everything else is hidden or unobservable. So that often gives us opportunities to simplify a Petri net by removing some of the things in the middle, as in this example. All that really matters is the output B follows the input of A. So we have a Petri net model for each of the 7 primitives I've shown you. I'll show you only the one for the merge for now because it's the simplest. Even though it's very simple, it's telling you something important. Concurrent inputs on A and B are a safety violation. The model expresses that condition by the firing rule, that if they both fired at the same time, you would have 2 tokens landing in the same place at the same time. And if you think about a merge as an exclusive OR, that's probably what you want. You wouldn't want to have both inputs changing at the same time, because then they'd either cancel each other or you'd get a glitch. So the Petri net model sort of expresses the range of acceptable or appropriate operating conditions. Anything that can lead to more than one token in the same place is a prohibited firing sequence. So why yes?
Are you saying that could you go?
Yes.
Yeah. Are you saying that if there's a token on A and a token on B?
A and B are transitions. I've had to draw them
they're transitions. Sorry.
thicker than regular transitions because they're labeled.
All right, so A and B can't both fire.
Well, they can, but if they did, then you'd be outside the range of conditions where you want to operate this device, and its behavior would be undefined. That's what this is saying.
Because you can only have one token in that white circle.
Yeah, that would be a safe marking. Okay. But about Petri nets, though, maybe not everybody likes Petri nets. Some people might prefer a state machine, so why am I harping about Petri nets? It's kind of an important reason. If you want to know the Petri net model for a combined circuit, you only have to combine the Petri net models of its components the same way those components are combined in the circuit. As in this example, we have a 3-way merge, and the Petri net model expresses the condition that any combination of inputs on any of the terminals would be a safety violation. We didn't have to make up a new rule for that. It follows as a natural consequence of the Petri net semantics. So we have this idea of compositionality, the whole being derivable from the parts. And why is this such a big deal, though? Because if you tried to do something similar to this with state machines, you would find that the state space of the combined system increases multiplicatively with the individual state spaces of the state machines and would quickly become infeasible. Whereas with Petri nets, your model of the circuit grows only in proportion to the size of the circuit that it's modeling. So it's a computational advantage here. Okay, so how do we do circuit analysis if we have circuits modeled by Petri nets? Pretty standard stuff. Let's say this Petri net represents a circuit. Not important what circuit it is for this example, just that it has transitions R1 and R2 enabled and tokens in those three places. Let's call this configuration the initial marking and draw it like this. If R1 fires, then we get a new marking where the top token moves over. Alternatively, if R2 fires, we get a different marking where the bottom token moves over. And this is already too hard to remember, so let's draw them like this. And if we notice in the lower two markings, there are more transitions that are enabled, so it seems like we should be able to continue in this vein. If we do that, we get to the reachability graph. And the reachability graph can be simplified by semantics preserving optimizations down to something like this. Or we could simplify it even more and get to the transducer model. In a transducer, the edges are labeled by I/O bursts. The idea is that if the circuit is in some state and it receives concurrently all of the inputs labeling one of the outgoing edges from that state in any order, it then changes to the state at the other end of that edge, and along the way, while it's changing, it concurrently emits the outputs labeling the edge. This is a more compact representation, but it also puts us on the way to learning something useful about the circuit. If we take a transducer model and we expand it if necessary to have at most one signal labeling each edge, we have something isomorphic to a state machine, and if we designate the accepting states as those whose outgoing edges are labeled only by input signals, the machine recognizes the quiescent traces of the circuit. Those are the traces leading to a point where the circuit will emit no further output unless it gets more input from the environment. And if we flesh this machine out with two more trap states, we have a machine that recognizes the union of the quiescent and the divergent traces. Divergences are those traces leading to undefined behavior. And we throw both kinds of traces together into the same set because we have to take the good with the bad when making comparisons. As you may know, comparing languages specified by finite automata is a solved problem. That means you can take two completely different looking circuits and test algorithmically whether they are behaviorally equivalent. Maybe even more amazingly, if someone claims to have improved a circuit by adding desirable features to it without breaking backward compatibility, even a claim like that can be made perfectly precise and tested algorithmically. If it holds, then we say there is a refinement relationship between the two circuits. And refinement is the same relationship that we want between a specification and its implementation. So what about specifications? If you design a circuit, you can theoretically draw the Petri net model of the behavior you want that circuit to have, and then test whether your circuit conforms to the Petri net model. But nobody wants to draw a Petri net, and even if someone did, the Petri net would be just as buggy as the circuit, so there's no point. But what you could do is write down a behavioral description of the circuit using these process combinators, of which you need only 7, and each of them has a very simple interpretation in terms of the effect that it has on a Petri net model. For example, input, output, sequential composition is just chaining one of them after the other. Parallel composition, let both of them run concurrently with shared inputs and outputs, or alternation means putting two Petri nets together in a way that allows only one of them to execute. So it's as if rather than drawing the Petri net by hand, you write down a description that is not only shorter and easier, but more likely to be what you have in mind, what you intend. Some examples. The first one, repetition, using the fixed combinator, which might be familiar to functional programmers, but otherwise let's just say it has something to do with recursion. This expression defines a control structure that makes any process repeat itself forever. We can use that in the next example of a specification for a process that waits for two concurrent inputs A and B and then transmits C and repeats that operation forever. Another example, a 4-phase handshake. Receive an input A, transmit B, do the same thing again, and we already have everything we need to specify an arbiter. That is, alternately engage in one of two possible 4-phase handshakes and repeat that operation forever. Once you get the hang of this, you can do more complicated examples. I'll show only one more. A knacking arbiter is like a regular arbiter, except instead of when a request is unsuccessful, instead of blocking it, it explicitly denies the request. You just have to write down the 4 handshake possibilities like this if you want. Just to mix things up a little, you could have a 4-phase grant cycle and a 2-phase deny cycle. And if your translator is a little bit sophisticated, it could also include functional programming operators like folding and map, just to make things more concise. And the young people these days aren't afraid of functional programming, so there's that. Okay, so we have our components. We have a concept of specification and verification. Seems like we should go ahead and start building some circuits now. I mentioned about the shunt primitive. The shunt primitive does a very simple thing. It either relays a signal from side to side or it relays it from top to bottom. But if it relays it from top to bottom, then the next one from the side also goes out the bottom, and then it goes back to normal. You can use a shunt to build a decision weight. A decision weight is supposed to have row inputs and column inputs, and it's supposed to receive a signal on one of each, and when it does, it acknowledges it from the output terminal that lines up with both of them. You can build decision weights by the yard, add on as many stages as you want. The idea will be that one of the shunts can receive the column input, which prepares it to receive the synchronized row and column input, which it will then route to the appropriate output. If you want multiple rows and columns in a decision weight, you can do that too. Set up one of these arrays. The column input prepares one of the columns to receive the synchronized row and column input. When it receives it, the cell that gets it directs the rest of the cells in the same column to clear themselves, and then it outputs. That means each cell has to be able to do one of three things. If it's not in the column that receives the column input, it just relays from left to right. If it is in that column and it receives next the signal from above telling it to clear itself, it does that and relays it down below. And if it's in the column and next it receives the row input, it initiates the signal down to the one below to clear itself. And then when it hears from the one above, it outputs. If you design a decision weight with an array of cells like this, it could get a little bit slow when there's a large number of rows and columns, but in that case you could save time by using this hierarchical decomposition that gives you a worst case logarithmic critical path. One more thing about decision weights. Sometimes we know in advance that not every output will be needed. We can cut costs by not having them. To do that, we have to, one way is to permute the rows and columns so as to clear a space in the lower right corner as best we can. Then we recursively implement the 3 non-empty quadrants and throw them behind a routing network like this. The recursion terminates when a quadrant reduces to a dense decision weight and can be implemented the normal way. It would be a little bit confusing to do this by hand because of all of the permutation networks involved. But you don't have to because there's an algorithm for it. So now let's talk about arbiters. We have a 2-input arbiter primitive, and we can use that to build arbiters with any number of inputs. As in this case here, it's very simple, but maybe not the best way because, as you can see, the critical path is proportional to the number of inputs. But if you want to improve on that a little, you can speed things up using this crossbar arrangement, which cuts it down to a log squared critical path, or you can use this tree. The idea of the tree is that each node in the tree arbitrates between its descendants and forwards a request on behalf of the winner to its parent. That would be linear space and logarithmic time. And one more alternative is a token ring. The token ring arbiter can kick this token around the ring, and only the one that holds the token can grant a request from the environment. A token ring arbiter could be linear time in the sense that the token has to go through linearly many cells, but the token ring is also unfair, and maybe that's not such a bad thing. Sometimes unfairness works to your advantage, like the way a CPU cache unfairly favors the most recently accessed memory location. In a token ring arbiter, the advantage is to the cell that is currently holding the token, which will be the one that has granted the most recent request. If you're interested in neural networks, I have a reference to a paper I can give at the end where someone argues in favor of token rings rather than trees for that use case. Anyway, one more twist on arbiters. You don't have to have a 4-phase handshaking port if you don't want to. You could have just 2-phase ports, as many as you want, and they all share one single request acknowledgement at the bottom, just by putting a regular arbiter inside of a wrapper like this and calling it a sequencer. Okay, so that's sort of a quick tour of what we do with these types of circuits. Now we have everything we need to talk about circuit synthesis, at least the raw materials. I mentioned about, with circuit synthesis, we try to get away from specifying every single connection in the circuit and then instead start with some high-level behavioral description and hope that we have some clever algorithm that will design the circuit for us. So state-based synthesis, which I'll talk about now, is not the algorithm I mentioned at the beginning, but a stepping stone to it. Typically, we'll start with a description, maybe in terms of process combinators, such as I've shown you. Often it's convenient to express it as a system of recurrences, as we have here. There is no real theoretical obstacle to translating this automatically into a transducer model. We find in this example that the transducer has 2 inputs and 2 states. That means we can implement it with a 2x2 decision weight, 1 row for each input and 1 column for each state, with the left column representing the initial state and initialized as such by the push. So if this gets an input of A, it's supposed to output C and stay in the initial state, which it does by reinitializing the left column. If it had to change to the other state, that would be a matter of initializing the other column. It could stay like that or go back to the beginning and so on. You can get pretty far just by knowing this trick, but it doesn't cover everything. If your specification allows concurrent inputs, then you'll need a sequencer on the front end. If it is not initially quiescent, then the push moves over to there. If it has non-deterministically concurrent inputs, then you'll need this extra feedback path. And there are loads of optimizations you can do on top of this that I won't have time to talk about. But I will talk about this non-deterministically concurrent input thing because it's kind of interesting. We have here a deceptively simple looking process, just inputs A and B. It's supposed to acknowledge A with X or B with Y. If it receives both of them together, though, it has the option of acknowledging them jointly with Z. What it doesn't get to decide for itself is, having received one input, whether it will wait for the other one. If it receives just one of them and the environment never sends another one, it must still acknowledge that input. That is the specification. Something like this could come up in a packet routing application where maybe during light traffic you send packets one at a time, but in heavy traffic you double them up. I have a reference to a paper about something like that as well that I can give at the end if anyone's interested. So anyway, the way to deal with this is you create a pair of feedback inputs and outputs for each input in the specification, and they are not exposed to the environment. They're just connected internally within the circuit. So the way this works is receives an input of A, it transmits A bang, then it waits for A question mark. When it receives A question mark, it transmits X, the same as if it just received A and transmitted X in the first place. On the other hand, if it receives B, it transmits B bang. Now it's waiting for B question mark, but before it gets B question mark, it gets an input of A. In that case, it can infer that these signals are concurrent and acknowledge them accordingly. It turns out there's an algorithm that'll take any transducer and transform it into the one that has all the necessary feedback signals you need. And then you can just go ahead and implement this the normal way, provided you have this feedback path that you see up here in the upper left. So where does that leave us? State-based synthesis is useful up to a point, but the cost of building the transducer model increases exponentially with the size of the specification. So it's limited in practice to fairly small specifications. And also, you can find examples where you could do a better job designing something by hand than this algorithm will give you. But it serves a useful purpose. Next, we're going to see a recursive algorithm for direct mapping synthesis. In a recursive algorithm, we try to break down a problem into smaller and smaller subproblems until we get to one that's so small that it's trivial to solve it in one step. State-based synthesis will play the trivial part of direct mapping synthesis, the part where the problem has been broken down so small that we're not even worried about this exponential cost. Okay, so here's what I'm really here to talk about today: direct mapping synthesis. All that up until now is just background material. With direct mapping synthesis, we don't try to build the transducer model or the reachability graph. We save the time and effort of enumerating the state space because we just use the PetriNet model, which can be done which can be generated efficiently even for a large specification. And we have a buffer for each transition and each place in the Petri net and a wire for each arc. We try to build a circuit that simulates the flow of tokens through the Petri net. And we might need some glue to interface them together. That will boil down to some combination of these four cases. First case, one transition connected to multiple places. That means if the transition fires, all of those places should be marked. So it makes sense to have a fork carrying a signal that broadcasts from the transition to its post-set places, telling them that they are marked. Another case, multiple transitions connected to a single place. That means if any one transition fires, the place should be marked. So it makes sense to use a merge network where the merge will carry a signal from any one transition to the place, telling it that it's marked. One more case, actually two more cases, multiple places connected to a single transition. That means we need all of those places to be marked before the transition can fire. So we use a join. When the join receives a signal from all of those places, it forwards one to the transition, telling it to fire. And one more case, a single transition connected, a single place connected to multiple transitions. That means if that place is marked, one of those transitions should fire. Which one? We'll leave that up to the angelic router. The angelic router takes a signal as input and sends it to wherever it can do the most good. For example, if there's a transition that can't fire because it's waiting for something else, but there's another transition that only needs one more signal to fire, then it sends it to the one that only needs one more. If you have multiple angelic routers in a circuit, they cooperate with one another to watch over the circuit and protect it from deadlock. Well, in case you haven't guessed, there's no such thing as an angelic router. So what does this mean? Are we stuck? Or am I just making it sound worse than it is? Maybe there's a way around it. Well, let's see. Suppose we're going to have some kind of token transfer negotiation protocol where transitions can request a token from a place and the place will grant or deny it, and it has arbitration and mutual exclusion and all that. What else could a place do but grant a token to the first transition that requests it and deny it from the rest, unless that first one has to change its mind because it couldn't get the rest of the tokens that it needed to fire? We end up with something like a dining philosopher's problem, only a lot worse. By the time all this contention is resolved, the chances of this, we can quibble about the math, but the chances of this making any progress are going to be pretty slim. In my opinion, this is still a dead end. So what could we do instead? Well, how about having a place that broadcasts a signal to its post-set transitions using a fork, but the signal doesn't mean go ahead and fire. It just means I have a token. You decide among yourselves who can make the best use of it. That means the transitions will have to confer by way of a channel that's not explicitly represented as a arc in the Petri net. But now that's looking much better because all we need is a peer-to-peer distributed consensus algorithm to be implemented in hardware. Some of you will say, challenge accepted, and I salute you. But what I'm going to do instead is arbitrate among the transitions using an external entity that I'll call a monitor. And we'll need one monitor for each subset of the transitions that have any preset places in common. Preferably not one for the whole Petri net because that would be a bottleneck, but it depends on the Petri net. So this means if I could describe this protocol between the monitor and the transitions, and if I could design a circuit for the transition, and if I could design one for the monitor, that would be the big finish. So let's start with the protocol. From the transitions point of view, it interfaces concurrently with 3 different buses. One of them comes from its preset places. Occasionally they send it notifications saying that they have a token, and the transition hopes to build up a full complement of these notifications someday. But while that's going on, it could receive a request from the monitor. And this request says, you know that token notification you just received? Pretend it never happened. Okay, fine. So the transition acknowledges the revocation request. It has one less token notification it can count on. But maybe if it waits, it'll get a replacement. And if it waits even longer, it will build up the full complement of them. And at this point, it requests a lock from the monitor. The monitor can either grant or deny the lock. If the monitor denies the lock, then the transition just waits until the next time it gets another revocation request, which it acts on and acknowledges. And now it doesn't have the full set of token notifications anymore, but if it waits, it might get a replacement and work up to the full set again, at which time it makes another lock request. This time, maybe it will be lucky and the lock will be granted. In that case, the transition forgets about all of the notifications it has received hitherto, releases the lock, and waits for the lock release to be acknowledged. At this point, we should also think of the transition as having fired, so there should be a signal going out to its post-set places telling them to be marked. But to keep it simple, we'll just wiretap this lock negotiation channel with a little box that sends a signal out to the places whenever the transition releases a lock. The lock negotiation channel is no big deal. Request, grant, release and fire, acknowledge. So, as for the monitor side of the protocol, the monitor mainly needs to arbitrate between multiple lock negotiation channels. Maybe not just 4 as in this example. And it could grant, deny, or block a lock request. Let's see an example of each. Suppose it's not doing anything. It receives this lock request from above. It might as well grant the lock, but before it grants the lock, it sends revocation requests to the transitions that are competing with the one that has requested the lock. These revocation requests say some of those tokens you've been notified about are no longer available to you because I'm letting this other transition use them. So when it hears back from the competing transitions that they've acknowledged the revocation, it's safe for it to grant the lock, which it does, waits for the lock to be released, and acknowledges the release. That's the easy case. When might it deny a lock request? Suppose now a request comes in from the left. It sends out the revocation requests to the others like before, and it receives revocation acknowledgments from above and below, but a lock request from the right. A transition should never acknowledge a revocation request with a lock request, but it could happen that the transition sent the lock request before it even received the revocation request. So this is the time when it's appropriate for the monitor to deny that request and then wait until it receives the revocation acknowledgement. At this point, it can then go ahead and grant the lock that it's been planning to grant. The lock is released and it acknowledges the release. So one more case. What about when it needs to block a lock request? This is a little bit more complicated, but let's see. Suppose it receives a request from the bottom. It sends out revocation requests to the other 3, and it gets back a revocation acknowledgement from the left, a lock request from the right, and nothing from above, because maybe the one above is a little bit slow. At this point, it can at least, while it's waiting, deny the lock request from the right, and then eventually it will receive the revocation acknowledgement from the right, and at this point at least that lock denial handshake is over with, but it still hasn't heard from the one above. Now while it's waiting, it gets another lock request from the right. What should it do now? It can't grant the request because it's already decided to grant a different one, and it can't deny it because if it denies it, the transition on the right will be waiting for a revocation request that's never coming. So what it does in this case is it just keeps it waiting for a short time until it finally hears from the one it's waiting to hear from above, and then it grants the lock below that it's been planning to grant. When that lock is released, it acknowledges the release, and concurrently with that, it also sends out the revocation requests on behalf of the transition on the right that has been waiting up until now but is now being served. So that sort of covers the protocol as best I can. What's left is to design the circuits for the transitions and the monitor. The design methodology for both of these is fairly similar, so because of time constraints, I'll talk only about the monitor. Now, designing this manually, something this complicated, would be difficult and we'd probably get it wrong. And even if we got it right, we would have to do it over and over again for each new Petri net that comes along, because it depends on how many transitions there are and how they're all connected. So it's best to take kind of a systematic or algorithmic approach to designing the monitor. And to that end, we take a step back and ask, what does it take to get a snapshot of what the monitor is up to at any point in time? And it boils down to these 4 sets of transitions with which it is interacting. We have the set D of transitions from which the monitor will have to deny a lock request if one comes along. The set B of blockable transitions. W, transitions from which it's waiting for a revocation acknowledgement. And the set G of transitions to which it will grant a lock when the required revocation acknowledgements have arrived. So we can package these 4 sets into a structure, as you see here, and build a graph of these structures, starting with the one where all 4 sets are empty and the edges are labeled by lists of processes. Now, why in the world and how should we do this? If you'll bear with me, the payoff to this will be an implementation for the monitor circuit, and I'll try to explain how first and then get to why. So before that, we'll define a few constants. For the ith transition, we have the set Ci of transitions that are competing with it, Ri of revocation requests sent when that transition requests a lock, the ith lock negotiation channel, and the revocation acknowledgement from the ith transition. If we know these things, then we can look at any vertex in the graph and infer the adjacent vertices to it in the graph, its neighbors, and then we can get the neighbors of the neighbors and so on until we've built the whole graph. That's the plan anyway. So how might that work? Suppose we start with some arbitrary vertex in the graph, say this one in the middle with these 4 sets. There might be a transition I that's not a member of any of those sets because it's not deniable, blockable, grantable, and it's not expected to send an acknowledgement. In that case, there must be an adjacent vertex where I is grantable, its competitors are deniable, and revocation acknowledgements are expected from its competitors, provided the monitor, having attained that configuration, has previously engaged in this interaction of receiving a lock request from the ith transition and issuing the revocation requests on its behalf. Another possibility, a transition I belonging to the set W from which a revocation acknowledgement is expected. Then there must be an adjacent vertex where no revocation acknowledgement is expected anymore from I. And if it was deniable before, it isn't now, but it is blockable. And to get there, the monitor must have previously received a revocation acknowledgement from the ith transition. Another alternative, the transition belonging to the set D of deniable transitions means there's an adjacent vertex in which it's not deniable, but it is blockable, and the monitor in that configuration must previously have engaged in this lock denial handshake. One more possibility, a transition I belonging to the set G of grantable transitions whose competitors, significantly, do not belong to the set W of transitions from which revocation acknowledgements are expected, meaning that it would be safe to grant a lock to that transition I. In that case, there must be an adjacent vertex where I is no longer grantable, its competitors are no longer blockable nor deniable, and to have reached that point, the monitor must have completed this successful 4-phase lock negotiation handshake with the ith transition. So that was a bit of a mouthful. I'll try to lighten up a little bit now. Let's see. That was the worst slide of the presentation, so it's all downhill from here. If we do this, we can take all of these vertices and we can throw them into this set G of pairs ME, where the left side M is a vertex in the graph and the right side is this adjacency set, which contains a set of pairs Pn, where the right side n is some vertex that's adjacent to M in the graph, and P is the list of processes labeling the edge from M to the adjacent vertex N. And we can go a little bit further and number all of these vertices from 0 up to however many there are in lexicographic order, so that the one where they're all empty sets comes first. And that sort of covers how to build the graph. But now, why? If you'll bear with me a little bit longer, suppose we just pull some pair ME out of this set and remembering that E is really this set of pairs of things representing outgoing edges from M, where each P is a list of processes labeling the edge, and N is an adjacent vertex to M. Just for the fun of it, we could let this object induce a function taking a list capital P of processes as an argument and returning a single process as a result. The process that it returns behaves as follows. It chooses one outgoing edge from the vertex M, and it participates in the processes labeling that edge sequentially, one after another. And after having done that, it just behaves exactly like one of the processes in its formal parameter capital P. Which process in P? The one indexed by the lexicographic ordinal of the adjacent vertex N at the other end of that edge. And we can clean this up a little bit with nicer notation, and we get this system of recurrences, one for each vertex in the graph. As such, it can be solved for a fixed point x, which for our purposes is a list of processes, such that if you apply some member hi of this ensemble to the list of processes x, you'll get back a process that is behaviorally equivalent to the ith term of x. And what good is all of this theoretical stuff in a talk that's supposed to be about circuits? Well, very good for us, because this process is none other than the specification of the monitor that we've been looking for, that we didn't have to write out by hand because it can be generated automatically by this mathematical construction. And better yet, given this specification, we can plug it into the state-based synthesis algorithm that I showed you before and get a circuit that implements the monitor without having to design and build it by hand and get it wrong. And furthermore, if we have to do it a bunch of times, it's no problem because it's done automatically. Okay, so how do we solve one of these recurrences? Well, ask me later at the end if you want to know. I'm not going to go through all of this because I'm just pointing out that it's no big deal, and compiler writers have known how to do this forever, solving one of these in terms of a fixed point combinator. Let's cut to the chase here. We have an algorithm DMS taking a process specification X. It depends on the state-based synthesis algorithm, SBS, which takes X and gives us back a circuit conforming to the behavior described by X. It also depends on something that some cost metric proxy that can be defined as anything we want, sort of a back-of-the-envelope calculation, anything that's really easy to compute, which gives us a very rough estimate of how costly it would be to compute state-based synthesis without actually doing it, because state-based synthesis can be very costly for large specifications. So we set this cost budget. We don't want to bite off more than we can chew. We set this value ks. It can have any units we want, maybe time or money or memory. That is the maximum amount of resources we're willing to devote to any particular instance of state-based synthesis. And if our estimated cost for the state-based synthesis is less than that, we'll just go ahead and do the implementation by state-based synthesis. But if it's more than that, is the interesting case. Then we have to split up the specification into smaller units that can be dealt with individually by this decomposition function upside down omega, which I haven't talked about and which I won't talk about because of lack of time. But if you knew what you were missing, you'd be glad I'm not talking about it, because it's a lot of boring bookkeeping stuff, mainly playing games with equivalence classes and figuring out how you can subdivide a Petri net into independent units, if you like. But anyway, once we've done that, we have this list of specifications y, and we have this combining form, which I also won't talk about, which takes an argument function f and applies f to each of the broken up pieces of the specification in y, and then puts them together into a circuit with more bookkeeping and so forth, but really nothing computationally expensive. the details of all of it are in a reference that I'm going to give in a moment. So, just for the sake of concreteness, we could say that our cost metric is the number of places in the Petri net. Anything up to 20 places can't possibly have more than 2 to the 20th markings. We can handle that. We'll just do that by state-based synthesis. If it's bigger than that, though, then we'll have to break it up. So although I've left out a lot of the details, I hope to have conveyed at least some sense of why I think this is amazing. The point is, you can take if you take any specification, no matter how big it is, and you can run this algorithm on it and be pretty well assured that the amount of work you'll do to synthesize the circuit will be proportional to the specification you started with. You won't get something blowing up on you with state explosion because you've set this budget. Anything above that will be subdivided and done separately. So you say you've broken it up and it's still too big. The monitor thing is too big that I showed you for state-based synthesis. You can do direct mapping synthesis even on the individual monitors and transition specifications that show up within your circuit. And so that's pretty much the bottom line here. You have circuits, you have chips with billions of transistors, and everyone's complaining they got to stay ahead of all that complexity. Think about this then. Okay, so as for the details I've left out, this first reference lays it all out for you in excruciating detail. Even if you want to write the code yourself, that's everything you need. That is my book. You can download it free, you don't have to buy it. The second reference, if you wanted to know about direct mapping synthesis up to the time that was published, it's a good place to start looking. Third one, I mentioned about token rings in neural networks. If you don't like anything else I've said, at least everyone loves neural networks, so you have something to take away from this talk. And the last one on the small packet problem, which comes up with the issue I mentioned with non-deterministically concurrent inputs. Some early work done on that with state-based synthesis, with TCP networks. You might want to chase up if you like that kind of thing. So that really brings to an end my prepared remarks. The angelic router thanks you, and I'm happy to take any questions that you might have in the time that's left. Anyone? Okay, well, then I'll just talk about what was brought up before. How would you really do a three-way voting machine? Well, like this, of course, obviously. 2 by 2 by 2 decision weight, three-dimensional decision weights. You can do decision weights with any number of dimensions as big as you want, and this isn't even the only way to do it. If I could talk all day about decision weights. But anyway, you have this thing, and you just consider every possibility. 3 no's make a no, 2 no's and a yes. That way, so on and so forth, up to 3 yeses. The point that was made is a very good one. You would need to have what we call a dual rail channel to do a voting machine properly in this style of circuit design. So there's that. Anything else? Yeah.
So the overall kind of recursive synthesis thing, you either have a leaf synthesis where you go for state-based, or you go for the other one where you split the problem, recurse, and then merge.
Yes, that's right.
So what's the asymptotic cost of that? Does it end up being sort of n log n, or like what's the kind of cost?
Well, you would set the if you take the cost of state-based synthesis to be a constant, I believe that the cost of doing the Petri net model, which is the only other thing, can be done more or less linearly in the length of the specification. it may be possible to construct an adversarial example where you have a transition or a monitor inside it whose state space turns out to be bigger than the overall circuit, but I can't think of how you would do that because the monitor increases only in proportion to the number of transitions it's interacting with, not the whole specification you started with, if you know what I'm saying. But I guess somebody who's better at that kind of stuff than I am could probably do a proper job of doing the exact algorithmic complexity analysis. What I've done a little bit, what I focused on, I guess, a little bit more is things like critical path analysis, which I think is probably the kind of thing that circuit designers care about more.
Because it feels like when you're doing, because you've effectively got a graph, which is your Petri, the current Petri net circuit you're trying to cut up.
Yes.
And presumably you could just partition it in a sort of just an arbitrary cut way, which would take time proportional to the number of nodes, but that's potentially, do you need to, would you typically do a sort of two-way split, or is it a multi-way split, or is it?
What you have to do is you have to look at the Petri net first and look at which transitions have any preset places in common. You form an equivalence class of transitions based on transitive closure of preset intersection. And then that gives you the basic units that you can subdivide the Petri net into. It won't work to just pick some arbitrary piece of it and pull it out. Once you've broken it up into what I call communities, I guess, because all the other words for that are taken. You have this community of Petri nets. Each community has this community of transitions, I'm sorry, and each community needs one monitor, and you go from there.
Okay, thanks very much.
Okay, thank you.